Hello, my name is Matt McGuire, and today I'll be analyzing this hairdryer, the Conair Ion Shine 1875, as my project for Engineering 3250 Thermodynamics. So as you can see, I've disassembled it here and laid out all the parts as best I can. So before I get into this, I'm going to go through here and briefly explain each disassembled part we have, what it's made of, and what general purpose it serves. That way, once we get into the analysis, we'll have all the background info already covered. Okay, so here starting from the left, we have the grill, or little blocker here, which is made of some light metal, and it's basically just a covering for the hole where the hot air is going to come out, mainly there for safety purposes. This next part here is the front housing, and this is just going to be comprised of some lightweight and heat-resistant plastic. Sometimes they use polypropylene, and it just needs to be resistant enough to not melt under heat, basically. The housing is going to house most of the elements of this hairdryer, but it's not going to serve much more of a function than just to hold everything in, as you can see. The next part here is the plastic casing. Again, this is just made of some nice lightweight heat-resistant plastic composite. The function it serves is connecting these parts back here all together. There's little screw holes you can see where the connecting screws will go in. And let's see. So this next part is pretty interesting. It's this cone-shaped piece here that will be the immediate enclosure of our heating coil element. Now this material that it's made of is called mica. It's a mineral that serves as an excellent heat insulator. So that's going to help protect that outer shell as well. And we'll see why this being an insulator is important later. Anyway, on to the next part, which is the heating element itself. So this is enclosed within the part here that we just talked about. I kind of have it spread out, but it's going to be made up of two mica boards attached together. You can kind of see here. They're actually attached at sort of a 90, well, not really, more like a 45-degree angle here. And so they're going to have coiled wires wrapped around it, as you can see, and these are heated by these electrical wires. Now, this coil itself is going to be made of nichrome, which is it's a metal with very high resistance. That's going to help those heat up. And again, that mica material is just going to serve as an insulator to withstand how hot these coils are going to get. And so we can see all these electrical wires coming in through the bottom here. Those are delivering the voltage needed to actually heat the coils. And you can see, if we look in the heating element, they're all connected to the mica material and then running obviously through the nichrome. And so that's where the heat of the coils is actually going to come from, is these electrical wires. Now let's look at where those wires come from before we keep moving on down the line. These wires are, obviously they're connected here to the main power cord, but we can see several switches here. This top one here is the cooling switch. Now we'll go over how that works in our analysis. So we'll get into that in more detail later, but this next one down here is the heat switch. So it's essentially a toggle. We can see on the back here different wire connections, and that's going to deliver how much voltage is going to be heated or going to be delivered to those coils. So let's see if we can switch that. Then the bottom switch here is a toggle for the motor, and this is going to determine how much voltage we deliver to the motor. We'll come back to that shortly when we talk to the motor. But here I want to talk about the main cord a little bit. So this is our main cord here, which it's going to connect to the outlet in your wall with this plug here. This plug, it says on here, can deliver 125 volts, 15 amps, so giving it a total power of 1,875 watts, or 1.875 kilowatts of power total. Interesting fact is, this is actually where the name of the hairdryer, the 1875, comes from that power. So it's going to have our plug here is going to have all the necessary safety features that we need, especially important because this is going to be used in very wet environments like bathrooms. So back up to the electric motor here, we'll take a look at it. It's going to operate like your typical electromagnetic motor, just using a magnet and delivered voltage to turn that crank. And you'll notice I actually had to cut some wires to get this separated so we could see. So usually it would be connected like this when in operation. And then these wires would connect all the way down here to that toggle switch we just looked at. And so the main power source from the cord here is being diverted between the motor and the heating coils. And that's why this device requires 1.875 kilowatts. Now that motor there, we're going to keep moving on. That motor is to drive the fan. You can see, just that fan is made of a lightweight molded plastic. It's connected to the motor shaft by a pin you can see here. And so what that's going to do actually is draw air in from the outside, which brings us to the final component, the back housing. Back housing would be connected onto the just right behind the fan here. And so we can see here it draws air in, and it's got this little screen here that keeps the user safe from sticking their hand in, getting it caught in the fan or anything like that. And that screen is actually, that's made of some kind of metal, but the back housing itself is just again made of a polypropylene plastic. And so then we can also just see these screws here, which they're going to connect the front housing and the back housing together. So that's pretty much the breakdown of the components. Now let's get into the thermodynamic analysis. We're going to be analyzing this system using the first law of thermodynamics. Now the first thing we're going to do is define the boundaries of our system. This is an open system, a control volume. So I'm going to draw my boundary starting right here over at the fan. And we're going to take this boundary all the way around the outside here, and then let's just cut our boundary right off above these switches here, as you can see, and bring it back around to the edge of the fan. Now I'm going to label these parts essentially for what they are in a thermodynamic sense, start thinking about them more technically. So over here, the outside surrounding is going to be our TC, our cold body. And then we have our fan here, which is basically just an axial flow design. It's basically fan blades drawing gas in, increasing the velocity. And then the motor here is a shaft that's going to be putting in work. So let's draw our work coming in. And that's going to be a negative value, since we know that the work is going into the system. Then our heating element here, this is our more work being put in. We're going to look at this basically like a heat exchanger, but again, we're going to have that negative value for work. And then finally, the shape of this mica shell and the housing put together, since that all is contained as one, we're just going to call that a nozzle because of the shape. And let's also draw our airflow here. So we have air coming in at TC, and it's going to be going through our system. And I don't quite have room for the arrow going out, but let's draw those just here at the edge, just to emphasize that's a bad arrow, what we're looking at. All right. So let's draw a quick schematic here showing our control volume. So we have our fan, and then we have our airflow going this way into our heat exchanger. And now the interesting thing about this heat exchanger is that it's actually contained within a nozzle. For simplicity's sake, we're going to draw this nozzle as separate, but just know that when we do our analysis, we're going to include the nozzle and the heat exchanger together as one device. And then we're going to draw that airflow out, redo our boundary as we showed before. Now, for states, I'm going to call the initial air entering over here state 1. Then I'm going to consider our heat exchanger and nozzle as one device, as I said, model them together. So then our state 2 is going to be at this other boundary here. And of course, we have our work coming in from our power outlet. And so that is our basic schematic. Okay, so before I go ahead and plug in values for our different scenarios, let's first run through our engineering model. So we obviously have an altogether open system at steady state, and this means our mass flow rate is going to be constant. We're dealing with air that we will treat as an ideal gas with a specific heat of 1.004 kilojoules per kilograms Kelvin. Now that specific heat value is the pretty commonly accepted standard for specific heat of air. Now we can also assume that our whole system is adiabatic, and therefore there's going to be no external heat transfer on the boundary of our device. We will also assume that all potential energy changes are negligible, just because we hardly have any elevation change going on here. And for this first analysis that we're going to do, where we're going to plug in all our values, let's say this hairdryer is running at highest possible heat and highest power level. That's going to give us some reliable data for our, it's going to give us some reliable data for our analysis. Let's also assume that our motor is 100% efficient and our heat exchanger is 100% efficient, so this is going to be an internally reversible process, an isentropic process. And so, there's our engineering model. Now we're ready to start our analysis. Now that we've got our engineering model assumptions, let's go ahead and assign some values to our states. So over here at state 1, we're going to assume normal room temp and atmospheric pressure, which we'll say is 20 degrees Celsius, which is 293 kelvins, and pressure as 1.013 bars, respectively. Now, specific enthalpy, that's going to be calculated by our specific heat times temperature 1. So I'm going to do all my calculations here on this marker board. That way we'll be able to have some room here on our board. So specific heat times temperature 1, and when we calculate that, that's going to come out to a specific enthalpy 1 of 294.172 kilojoules per kilograms. So keep that number in the back of our minds. We can also do another calculation to solve for specific volume. Since we're assuming the ideal gas model, PV equals RT, we'll manipulate that to solve for specific volume, and we get a value of 0.826 cubic meters per kilogram. Now, what I've also done is, for our inlet area, I measured the cross-sectional area of the fan, since that's right inside our boundary. And so what we're going to do with that is first calculate volumetric flow rate. So the area 1, is, I measured that to be 62.07 cubic centimeter, centimeters squared. Then we're going to combine that with our assumed inlet velocity of 0.1 meters per second. Now I looked up that value as normal air velocity in a room, and since it's right before it hits the fan, we're going to assume velocity 1 to be 0.1 meters per second. Now, combining that, we're going to get a volumetric flow rate of 0.062 cubic meters per second. So, what we're going to do next, hold on, let me write down these values here so that we don't have all these messy calculations on our board. So, volumetric flow rate we found is 0.062 cubic meters per second. Now that we have all these values, we're going to find our mass flow rate. So, we know that mass flow rate is volumetric flow rate divided by specific volume. That's going to come out to 0.075 kilograms per second. Write that value in. Now let's recall that because our system is steady state, we can run a mass balance also for our one inlet, one outlet control volume, which we're going to do. Mass flow rate of 1 plus mass flow rate of 2 must equal 0. Therefore, our mass flow rate must, our inlet mass flow rate must equal our exit mass flow rate, and that's going to have to be for all mass flow rates in between. Now, this will be key to analyzing the rest of our system. The next thing we're going to do is plug in our values at state 2. So I did a little bit of research and found that at full power, the air leaving the dryer, the hair dryer, is going to be about 45 degrees Celsius, which is 318 kelvins. And it's going to be moving at 22 meters per second. Again, this is just some research I did. Now, we know that if we take our specific volume times our temperature, that we're going to get specific enthalpy. So let's calculate our specific enthalpy at state 2 by doing just that. And we're going to get a value of 319.272 kilojoules per kilograms. It fits over there. Alright, now I measured the exit area to be 13.38 centimeters squared. So again, let's go ahead and combine that area. 13.38 centimeters squared. Let's combine that with our exit velocity to find our exit volumetric flow rate, which will be 2.943, doesn't look like a 3, meters cubed per second. Now, here's the interesting thing. We can't get our specific volume yet since we don't know the pressure. So we have two unknowns, which are specific volume at state 2 and pressure at state 2. What we're going to have to do is get creative and manipulate our equation for mass flow rate. So let's go ahead and write out that equation. We're going to get creative with that and manipulate so that we can solve for V2. We know the rest of these values. So that's going to be volumetric flow rate divided by mass flow rate. Remember, steady state, our mass flow rate's equal. For V2, we're going to get a value of 39.24 meters cubed per kilogram. So I'm predicting this causing a very low P2. Let's find out what it is. Solve for P2 by manipulating that ideal gas equation again. PV equals RT. So our P2 is going to equal 2.33 kilopascals, or 0.233 bars. So that's a very low pressure, because we all have all this air being pushed out here at the end with a very high velocity. Okay, so what I've done is written out some of those values we found here at our different states. And now we're going to go ahead and analyze this system by following the first, make sure it follows the first law of thermodynamics. And so here's our equation for energy balance of an open system at steady state. So 0 equals Q dot minus W plus mass flow rate times H1 minus H2 plus V1 velocity 1 squared minus velocity 2 squared over 2 plus change in potential energy. Alright, what we can cancel, first of all, we can cancel heat because we know that this is adiabatic. We can cancel potential energy. We established that at the beginning. Now, because of the heat exchanger and nozzle considerations that we're doing, we're going to keep the rest of these terms. Now, our work in is going to be all of that work coming, all that electrical work coming in. So I'm going to write down here work total as 1.875 kilowatts, and it's being distributed throughout our motor and then through our heat exchanger, and it's all going up in there. And so I'm going to go ahead and rewrite this equation here, just simplified. That way we can run our calculations. Now, from my research, I found most hairdryers use about, most hairdryer motors, they use about 14 watts, which, if you think about this hairdryer has 1.875 kilowatts of power. That's a huge amount of the energy that's mostly going towards the heating element, while only a little bit of power is going to be going to the motor. So since we're all analyzing this as one system, that doesn't concern us as much. We're just concerned about the amount of work going in, but it's still interesting to think about. I just brought it up to a separate board just to see it easier. And we have 0. What I was going to say is plugging in units here, I'm going to pretty much do it like base units, just so it's easier to see everything as far as how the units work. So kilojoules per second is actually going to be kilograms times meters squared per second squared per second. Then we have plus our mass flow rate, which we found to be 0.075 kilograms per second. This is times change in enthalpy. For change in enthalpy, I'm going to do it as specific heat times change in temperature. So we know that that's, if we convert to just joules, we 1004 kilograms per meters squared per second squared. That's kilojoules over kilograms per Kelvin. That's a little messy, but we'll work with it. And then I don't think I can fit the temperature change in there. Temperature change is 25 kelvins. Okay, so that's being multiplied by that. Then we have our change in kinetic energy, which we know from our entrance velocity, 0.1 meters per second squared minus 22. Oh, I'll put the, oops. I'll put the units outside. That's over 2. All right, now before we go ahead and plug in our numbers, let's make sure our units actually work out. We know that kelvins is going to cancel. Kilograms right here is going to cancel. Let's see. we got kilograms, meters squared per seconds cubed, and then all of this kilograms, meters squared per seconds cubed, right? Multiplying over here, kilograms per meters squared per seconds cubed. Boom, that works out. So plugging in all of this, we get 0 joules on the left side and negative 10.65 joules on the right side. Now, in a perfect energy balance with steady state, we should get 0 equals 0. But we have a little discrepancy here with a little extra energy coming in. Now, this is obviously in real life calculations. We don't get 100% accuracy, but these little errors, which the error is less than 5% anyway, which is usually the science community's notation for we can let it be 0 essentially. But reasons for this could have been error in measuring, or perhaps some small heat transfer not accounted for, and then of course friction with the motor that could have been happening. There's lots of little quirks that we get in real life calculations, but I'd say this final energy balance here is pretty good. So that's looking at it from a perspective of the hairdryers on full blast and full heat. And now let's take a look at what happens with some other different scenarios. Okay, so our second scenario, if we reduce the fan power using this bottom switch here, so say it's on the top switch and we move it down, then that means our outlet velocity is going to be less than our previous outlet velocity with the full power, and we're going to have a smaller mass flow rate than before, as well as a smaller change in kinetic energy because of the smaller change in velocity. Now let's move on to a different scenario. For sake of time, I'm not going to run all those calculations specifically, but just getting a conceptual idea here. So say we change our heat level. So say we have our heat level switch at the top, we want less heat, we turn it down. Well, then what's going to happen is it's going to make change our outlet temperature less than our inlet temperature, and we're going to have a smaller change in enthalpy just because the discrepancy between the inlet and outlet temperature is less. And by my 2's and 1's here, my numbers, I'm meaning scenarios, not states specifically. So actually this would be the third scenario, so I should label that with a 3, put that as a 1. So that's what would happen with the third scenario. Let's look at a fourth scenario here. And we talked about this cooling switch earlier. So this cooling switch is very interesting. It's essentially just a switch that can cut power to the heating element. So it's not actually adding cool air when you turn this on, but what it's really doing is letting the air flow through without the heating coils heating it. And what this means is that it's essentially an isothermal process. It makes our outlet temperature very close to our room temperature, so I'll just label that as T1, and the only enthalpy change that we'd account for would be enthalpy change because of nozzle. And we know that usually the nozzle is not going to have, especially one where the entrance and exit area, there's not much discrepancy. There's really not going to be much of a temperature or enthalpy change when that's our only thing changing. So essentially that's why this is almost an isothermal process. And of course kinetic energy remains constant because the change in kinetic energy of this fourth scenario is equal to our change in kinetic energy of the third scenario, because when we turn on that cool button, we're not messing with the motor at all. We're just turning off the heating coils. So there's our 4 scenarios of how this hairdryer would operate. This has been an analysis of the hairdryer from a thermodynamics perspective. All resources used are shown at the end of this video and linked below. I hope you've enjoyed this video. Bye now.